times c. I'm going to offset something here for a second. And I'm sure everyone remembers this from 200A.
I saw it and I thought it was volume.
Frequency equals h over mv, where v is velocity. Oh, by chance, remember what that was called. This would have been like probably week 1 or 2. I'm sure, you know, that's at the top of our head still.
De Broglie. Oh yeah.
The de Broglie wavelength.
What's that mean? Massive electron?
Yeah, over here we're talking about massive electron. Here we're talking about the de Broglie wavelength. And I'm just going to put that as an offset here because, well, I should say, depending on how you first semester, you may not really cover it that much. But the de Broglie wavelength itself is how we can calculate the wavelength of any matter. Meaning that you could, if you know your own mass in kilograms, you can calculate your own wavelength.
Gosh.
If you have a baseball, you can calculate the wavelength of a baseball.
So lambda is wavelength?
Right, yes. Now, the de Broglie wavelength for ordinary matter is irrelevant. The wavelength of a person is like 10 to the negative 30th meters. But when we're talking about particles, especially stuff that has a very high velocity, then it does become relevant. And that's why an electron can also be a particle or a wave, because its wavelength is close to its actual size. And that's actually what we're going to calculate here. An electron moving at the speed of light, what's its wavelength?
That of light?
Well, essentially, in a way of looking at it, but what kind of light? Well, we already know it's gamma, that's what we...
Yeah.
Oh, now here's another good one. What's H?
Planck's constant.
Is that
Planck's constant, and it's equal to?
6.2626 times 10 to the negative 34.
Yes. Except one of those twos was extra.
Yeah, I said it on accident.
where do you get that from?
6.6
From the back of his mind.
times 10 to the negative 34 joules times seconds. Where do you get that from? Yeah, and it's still floating around.
I have my calculator.
A constant that's still out there. Do you have H bar in there too?
I have a bunch of random constants.
Okay, sometimes there's H, but then there's also another one, H bar, like that, which is H over 2 pi, I believe.
No, I'm Planck's constant.
Just that one? Okay. Massive electron, I had that written down, and then I've...
9.109 times 10 to the negative 31.
Yeah. And I had that one on the previous line. And then 2.9979 times 10 to the 8 meters per second.
Why do you use that many digits instead of just 3.00?
Because these both have 4 sig figs.
Oh, okay.
Mostly why round off unnecessarily.
That's how the online homework does it. Nobody likes that.
Their system's much more annoying than some of the other ones too. Some of the other ones like basically build the rounding in, so they'll give it to you if it's like 2 or 3 numbers off. So ultimately we calculate a wavelength, so the gamma ray released is 2.43, well, each gamma ray releases 2, it's 2.43 times 10 to the 12 meters. Or another way of looking at this is the wavelength of an electron is that same wavelength there, 2.43 picomers. Which is also then why the wavelength of subatomic particles is relevant, because that's on the order of its size. And it's also why we can't accurately measure both its position and its momentum. Because since it's acting as a particle or a wave, we can't really know entirely both properties at once. Because its wavelength is large enough to be on the size of the particle itself, or close enough to it. So a whole bunch of weird subatomic physics stuff that, you know, we can calculate without having to really understand what's going on here, and that's kind of all we're doing, seeing what we can calculate out of it. All right, so that's more E equals mc squared. I could have sworn I had another one in here. Oh, it's a couple slides down, so we'll do one more version of this later. But any other questions on where we got it so far?
Yeah, what the heck?
What's that?
What the heck?
Yeah, that's a pretty good one. Well, I mean, it's one of those where it's like, it doesn't make sense, but that's kind of the most important part of it is that it doesn't make sense.
Yeah.
I mean, it's weird to say it that way, but it's important that it doesn't make sense. Because that means that, because if it was so intuitive that it was easy to figure out,
Everybody would do it.
then yeah, everyone would know it already.
Yeah.
I mean, this stuff is, it's still been confusing for 80, 90 years already. The math has been worked out for a good amount of it, but there's still a lot of unexplained stuff. Like, what is an electron? We can calculate all this information here, we still can't really say what it is. Go to Wikipedia, it'll say it's a fundamental particle. That doesn't really tell you much.
Yeah.
All right, beyond all that, let's go a little bit more into some of these nuclear processes. So we mentioned fusion versus fission. Let's kind of define these a little bit more here.